Question 13, 14. A block attached to a horizontal spring is pulled to the right a distance of 18 centimeters from the equilibrium position. The block is released and the block spring system undergoes simple harmonic motion at frequency 1.25 Hz. Assuming that positive is to the right, determine at 0.1 second after release the block's A displacement, B velocity, C acceleration. This is the point of equilibrium. So the box. So if this is 18 centimeters, then here we have the frequency F as 1.25 Hertz. We have the amplitude 0.18 meter. My function here this is my A minus. So at t equals 0, this point was here. So my function here is a cosine function, and I have x equals to a cosine omega t. So if I substitute omega with 2 pi f, then omega equals to 2 pi times 1.25. Omega is 2.5 pi radians per second. So watch out for the unit of the omega. It's radians per second, which means when you substitute it in the here in the function, multiplied by times seconds, it will give you a phase of radians unit. So here I have x equals to 0.18 cosine 2.5 pi t. Now at t 0.1 seconds, I have x equals to now this one's going to be radians. So make sure your calculator is set up with the right unit of the phase. Or you can convert this one to degrees by multiplying by 180, dividing by pi, you will get degrees. Here x equals to 0.1273 meter, or x equals to 12.73 centimeters. B, we need the velocity. We know that the velocity v is the time derivative of the displacement, which means v equals to, this is the function for the displacement, then if you take the derivative of cosine is minus sine, so I have minus 0.18 times 2.5 pi sine 2.5 pi t, and the function would be minus 0.45 pi sine 2.5 pi t. This is the function. Now at t equal 0.1 second, I have v equals to, again, minus 0.45 pi sine 2.5 pi 0.1. Then v is minus 99.9 seconds centimeter per second, or you can say here v equals to meter per second. This one is minus 99.96 centimeter per second. C, acceleration, as the second derivative of the displacement, or derivative of the velocity, and in this case, if this is the function of the velocity v, then the acceleration a is going to be minus 0.45 pi times 2.5 pi. Again, this is going to come back again to the cosine, 2.5 pi t. And the acceleration is minus 11.1 cosine 2.5 pi t. Then at t equals to 0.1 second, I have a as minus 11.1 cosine 2.5 pi as 7.8 meter per second squared, or a is minus 7.8 10 to the power 2 meter per second squared. 1339. Question 1339 reads the following. Sound waves used to determine the depth of water in a lake are emitted from a boat with a period of 2.5 10 to the power minus 5 seconds The wavelength of the waves in the water is 3.8 10 to the power minus 2 meter, and the reflected pulse is received 9.6 10 to the power minus 2 seconds after the pulse is emitted. A. Determine the speed of the pulse in the water. B. How deep is the lake at that location? Okay, so in this case, what do we know? We know that the period is 2.5 10 to the power minus 5 seconds. We know that the lambda is 3.8 10 to the power minus 2 meter, and the time of the pulse 9.6 second. This is the time the pulse takes. So this is my boat. Then the time the pulse takes to go all the way and come back is 9.6 10 to the power minus 2 seconds. We know the speed c equals to f times lambda, where f is 1 over t, so c is lambda over t. We have lambda 3.8 10 to the power minus 2 divided by 2.5 10 to the power minus 5, and c is 1.52 10 to the power 3 meter per second. So this is A. B, we need to calculate the distance between the boat and the bottom of the lake. Now, this time is the time the pulse takes from this point 1 going to point 2 and then coming back to point 1. So 2 trips all the way from the boat to the bottom of the lake and back from the bottom of the lake to the boat. The total is 9.6 to the power minus 2. So the time the wave takes from the boat till it reaches the bottom of the lake is half this time. So if I put D equals to V times T, then this D times 9.6 to the power minus 2, all divided by 2. And in this case, D is 72.96 meter. Question 1352. The question reads the following. The distance between nodes on a standing wave pattern on a certain string is 16 centimeter. So the distance between the nodes in a string that is binding from both sides is 16 centimeter, which basically means for the case of the string, I have lambda over 2 equals to 16 centimeter. There are 5 nodes between the ends of the string, which means if I take this end and this end, this is the one that is moving up and down. as the two ends, then I have 5 nodes in between. Which means I have 7 nodes in total. So I have here 1, 2, 3, 4, 5, 6, 7. So those are 7 nodes in total. This is the one that is going up and down in a very small displacement, such that we're considering it here. It's a node. So we have the function. Okay, so this is what we're gonna see, such that we have 5 nodes in between those two end nodes. So the number of the nodes in total would be 7. Now the question says a single wave takes 1.2 seconds to travel to one end of the rope and back again. So it takes 1.2 to go all the way from one end to the end and come back again. A, what is the wavelength of the waves producing the pattern? So we want to calculate the wavelength. So if we know that the distance between any two nodes is 16 centimeters, this means lambda is 32 centimeters. Then B, how long is the rope? How long is the rope? Between two nodes is lambda over 2. I have here 1, 2, 3, 4, 5, 6 sections. So I have L equals 2, 6 times lambda over 2. In this case, L equals 2, 6 times 32 over 2. L equals to 96 centimeters. C, what is the speed of the waves? The speed of the wave can be calculated either using F lambda or D equals to C times T. If we want to calculate it with F lambda, then what do we know? We know lambda, the frequency here. We know the period here from this point to this point. How? We know that it takes 1.2 seconds to go all the way from one end and come back to the same end, which means the one trip is 0.6 seconds. 0.6 seconds for how many lambdas I have here from this point to this point is 1 lambda, to this point is 2 lambda, to the end is 3 lambdas. So 3 lambdas, so the period for 3t equals to 1.2 divided by 2. Then t is 0.6 divided by 3, which is 0.2 seconds. So the period for one wavelength is 0.2 seconds, which means the frequency, we need this one and the next one, is 5 hertz. Then C is 5 times lambda, which is 0.32. Then C equals to 1.6 meter per second. Or you can calculate it using the D equals to CT. D is the length of the rope. I have 96.96 equals to, we need the speed, C times T. T is the distance it goes for one length of a rope, which is from one end to another. If we have the time from one end to the other end and coming back 1.2, then it would be 1.2 over 2. This is for one end to another. In this case, C equals to 0.96 times 2 divided by 1.2. C is 1.6 meter per second. So either way, we can calculate the speed. So this was C. D. What is the frequency? We calculated the frequency earlier. However, if you calculate the speed first, then you know that the frequency is times lambda equals to the speed, which means that the frequency is C divided by lambda, 1.6 divided by lambda, which is 0.32. F would be 5 hertz. E, the mode. What harmonic is this? If you count the antinodes, 1, 2, 3, 4, 5, 6. So this is the sixth harmonics. Study guide 8, self-test 2, question 2. So in this question, we have the following. A standing wave of equation y as minus 6 cosine 6t sine 4x is formed from a reflected wave moving in the positive direction. So my reflected wave is moving in the positive direction. I will assume it is A sine omega t, positive direction, which means minus beta x. and an incident wave moving in the negative direction of x. So I have here incident in the negative direction. The sign of the amplitude will be different, but doesn't mean that this one will be negative. It may be positive. We'll see. Omega t negative direction means plus beta x. So those are the incident wave and reflected wave. Again, we assume that this one is A. However, one of them has the opposite in sign than the other, to have a zero at the node at the end, either ends. So in this case, if we take this reflected wave, add it to the incident wave, what do I get? I get A sine omega t minus beta x minus A sine omega t plus beta x. Now, if I rearrange such that this one first and this one comes second, then y reflected plus y incident becomes minus A sine omega t plus beta x minus sine omega t minus beta x. This is how the two functions are going to be added. Then if I use the trigonometric identity, that is sine A minus sine B equals 2, will be 2 cosine the summation A plus B divided by 2 sine the difference A minus B divided by 2. So if you use this one on those two signs, then reflected plus y incident equals to minus A, then 2 cosine omega t plus beta x plus omega t minus beta x sine 2 omega t plus beta x minus omega t plus beta x. Then y reflected plus y incident equals 2. So here beta x with beta x will cancel. Here omega t with omega t will cancel. So I end up with minus 2a. Omega t plus omega t is 2 omega t divided by 2 is omega t cosine omega t sine beta x plus beta x is 2 beta x divided by 2 is beta x. I also know that y reflected plus y incident from the equation that was given to me equals to minus 6 cosine 60 sine for x Now if I equate those are equal. Yeah, beta is x as k also. Yeah, you're right. I can. Sometimes we use beta, sometimes. I'm glad that you told me. Okay, so beta is used in other books for also in wave propagations, in waves. But here we'll use the wave number k. It's the same. It's not going to change anything. So at the end, I will get those two equations. Now, if I equate those two equations, what do I get? I get minus 2a cosine omega t sine kx equals to minus 6 cosine 60 sine kx. So in this case, I have minus 2a equals to minus 6, which means a is 3. I have omega t equals to 60 omega 6. I have kx equals to x, which means k equals to 4. So now I can rewrite every function. The incident reflected, so the reflected is y reflected is 3 sine 60 minus 4x. Y incident as minus 3 sine 60 is 4x. So this is how we find the amplitude for the reflected and the incident. It's interesting to notice that the one that is going in the positive direction is the one that's having the positive amplitude, and the one that is going in the negative direction is the one that's having the negative amplitude. 13, 50. In 1350, the question reads the following: the speed of a wave on a 6.2 meter long rope is 7.6 meter per second. So I have L equals to 6.2 meter rope. I have the speed as 7.6 meter per second. Determine the frequency of oscillation required to produce standing wave pattern having A, 1 antinode, B, 2 antinodes, and C, 3 antinodes. If we have one antinode, this means I have L equals to 1 for one antinode. I have frequency being the fundamental, and then N is 1. So L equals to lambda over 2. And then we call this one lambda 1. then lambda 1 becomes 2L 6.2 times 2, which means lambda 1 equals to 12.4 meter. And in this case, F1 would be C over lambda 1. F1 equals to 7.6 C divided by lambda 1, which is 12.4, and F1 is 0.613 hertz. So this is for one antinode. For two antinodes, I have L equals to 2 lambda over 2. Let me call this one lambda 2. So lambda 2 equals L, or lambda 2 in this case is 6.2. So if lambda 2 is 6.2, then F2 is C over lambda 2. F2 is 7.6 divided by lambda 2, which is 6.2. And in this case, F2 is 1.23 hertz. For 3 antinodes, we have L equals to 3 over 2, or let me call this one lambda 3, or lambda 3 equals to 2L divided by 3. Lambda 3 is 4.13 meter. In this case, F3 has C over lambda 3. F3 equals to 7.6 divided by 4.13, and F3 equals to 1.84 hertz. So if you compare those to frequencies, so let's look at those frequencies. So what do we have here? We have 0.613. We have this is the fundamental frequency. Then we have the second harmonic, 1.23 hertz. Then we have the third harmonic, 1.84 hertz. What is the relationship between those frequencies? Remember, 0.613 is the fundamental frequency, the first harmonic. If you multiply it by 2, it's going to give you 1.226, which is 1.23 hertz, which is the next harmonic, the second harmonic. Now, if you multiply this fundamental by 3, 0.613 times 3 is going to give you the 1.84, which is the third harmonic. Question 1316 reads, at a time of 100 seconds, after starting its simple harmonic motion from maximum displacement, which means we have here a cosine function, and we're starting from maximum, which means it's a positive amplitude of omega t. So the displacement is 2.5, which is the amplitude here is 2.5 centimeters. If the frequency of the simple harmonic motion is 2.8 hertz, what is the amplitude of the simple harmonic motion? So this is not the amplitude, this is the amplitude, or this is x equals to 2.5 at t equals to 1 × 10⁻² seconds. We need to find the amplitude. So here, this is the function. Omega is 2 pi f, 2 pi times 2.8. Omega is 5.6 pi radians per second. So I have now the omega. I found the omega. I need the amplitude. He gave me the displacement that corresponds to the time. So now I will substitute x with 0.5, 10⁻² equals to a. I don't know a. Cosine omega is 5.6 pi times 1, 2. Then the amplitude A equals to 2.5 10⁻² divided by cosine 560 pi. Now be careful that this one is radians. The amplitude is 2.5 10⁻² meter.